Hello friends, welcome to my channel PH Chemistry. Today we are going to discuss Baeyer-Villiger oxidation. So in this video we are going to understand what is Baeyer-Villiger oxidation, what is the mechanism of this reaction. We'll understand some examples related to this reaction, and lastly we'll get the tricks. What are the tricks related to this reaction? So let's get started. We'll see what is the Baeyer-Villiger reaction. So in this reaction basically ester is prepared using ketone. We'll write a general reaction like we'll take this general ketone. The reagent used in this reaction is per acid. So the per acid is, we'll write a general per acid, and the product we'll get is like this. So the reactant is ketone. Reagent we are using is per oxide or per acid, and the product is ester. So first we'll understand what is per acid. Per acid is anyone which is having oxygen-oxygen linkage. So oxygen-oxygen linkage is called as per linkage. So this is the per acid. So what are the reagents used in this reaction? As I told you, any per acid we can use. The most common per acid which we know is hydrogen peroxide, H2O2. And the most common per acid which is used for this reaction is metachloroperbenzoic acid. Shortly it is known as MCPBA. Okay, so in most of the cases you have seen this MCPBA as a reagent. So it is nothing but chlorine at meta position. Per means here we are having oxygen-oxygen linkage. So per benzoic acid. So this is our benzoic acid. Okay. So metachloroperbenzoic acid, this is the reagent used in this reaction. So if R and R dash in this reaction are same, that is if we are having a symmetrical ketone, then there is no question of migratory aptitude. Okay, the product we'll get is only one ester. What if R and R dash groups are different? That is, if we are having an unsymmetrical ketone, in that case migratory aptitude comes in action. So the migratory aptitude for the Baeyer-Villiger oxidation is phenyl, then hydrogen, and then any alkyl group. For alkyl group, the migratory aptitude is tertiary, then secondary, and then primary, and then CH3. Okay, so this is the migratory aptitude for the Baeyer-Villiger oxidation. This migratory aptitude will decide which group will attach to oxygen and which group will attach to this carbonyl. Okay, so now we'll see the mechanism. So to understand the mechanism, we'll take one specific example. Here I am taking methylphenyl ketone, and the reagent which we are using is metachloroperbenzoic acid. Okay, so this oxygen is having lone pairs. As lone pairs are having higher energy as compared to the pi bonds, these lone pair will take this hydrogen of MCPBA. So when this lone pair will take this hydrogen, negative charge will shift here. So what we'll get is this OH will attach to hydrogen, and as here you can see oxygen has three valencies, three bonds attached, so positive charge will come here, and the remaining is a reagent with negative charge. Now what will happen, this negative charge will attack on the electrophilic carbon and this will restore. So the product we are getting is OH Me. This oxygen is attached to this electrophilic carbon. Chlorine is present on the meta position. But now you can see here heteroatoms are attached with each other. So oxygen is having two lone pairs. Here this oxygen is having two lone pairs. There is a maximum repulsion between the lone pairs of two oxygens. So this oxygen-oxygen bond will break. This double bond will come here, and Now the question of the migratory aptitude, that which group will migrate, either Me will migrate or phenyl will migrate. As we discussed in migratory aptitude, that migratory aptitude of phenyl is greater than hydrogen, which is greater than methyl. So here phenyl will migrate first. When these lone pairs come here, this phenyl will shift to this oxygen, and this oxygen oxygen linkage, that is per linkage, will break. So what we are getting is this phenyl attached to oxygen, this oxygen is attached to OH and Me, here positive charge comes, and the remaining is this. Okay, so now this negative charge will take this proton, so our final product is the ester, and the byproduct is metachlorobenzoic acid. This is metachlorobenzoic acid, and this is our ester. Its name is phenyl acetate. So in this way the mechanism will work. You can take a screenshot. I'll pause the video for 2 minutes. You'll take the screenshot of it. Okay. So now we are going to discuss some examples of Baeyer-Villiger oxidation. So first example is, you can see here, simply what you have to do is, you just see the migratory aptitude and attach oxygen to that. So here you can see this is the tertiary carbon and this is CH3. So as I told you in the migratory aptitude, what is the migratory aptitude? Tertiary carbon is having more than secondary, then primary carbon, and then CH3. So in this reaction, this will get attached to oxygen. So what will be the product? Just pause the video for 2 seconds and think yourself what should be the product of this reaction. So the product is like this. So this is the product. This is ester. Simply what you have to do is just attach oxygen to the group which is having more migratory aptitude. This is the trick number 1. Okay, this is the trick number 1. What is the trick number 1? Just attach oxygen to the group which is having more migratory aptitude. Okay, so our second example is, here you can see the stereochemistry comes in question. So first we'll understand the migratory aptitude. So which carbon is this? Which type of carbon is this? It is attached to 3 different groups. So it is tertiary type of carbon, and again this is CH3. Similar situation is there. So just we are going to attach oxygen to this. Okay. First I'll ignore the stereochemistry. Just I'll attach oxygen to it. Now here comes the trick number 2, that the stereochemistry in the Baeyer-Villiger oxidation will remain same. So we keep these groups as it is. So here comes trick number 2. So what is trick number 2? Stereochemistry in the Baeyer-Villiger oxidation will not change in the product. It will remain as it is. So third example is, you can see here there is no ketone. It is a aldehyde. So this is phenyl and this is hydrogen. According to migratory aptitude, we have seen phenyl is having more migratory aptitude than hydrogen and then methyl. So according to this rule, phenyl should attach to oxygen, but the correct answer here is this. So what is the reason? Here comes the trick number 3. Here comes trick 3. What is trick 3? Whenever aldehyde is present, the product will always be acid by default. When you see aldehyde in the reactant and this per acid as a reagent like MCPBA, the product will always be acid. To diketone with MCPBA, the product is always anhydride. Product is always anhydride. This is the trick number 4. This is the non-Borneo system. Non-Borneo system. Just apply the migratory aptitude here. This is the tertiary carbon, this is secondary carbon. So according to migratory aptitude, oxygen will get attached to the tertiary carbon. So our product is like this. So, okay, so this is our product. Next example is this. Here this is the tertiary carbon, this is secondary carbon. So the product you expect is, the expected product is, so oxygen should attach to the tertiary carbon. This is expected, but this is not the product in this reaction. The actual product of this reaction is this. Why this is the actual product of reaction? According to migratory aptitude, oxygen should attach to tertiary carbon. This should be the product. What is trick number 5? Trick number 5 is, whenever steric hindrance is present, migratory aptitude will not work. Okay, so here you can see there are two paths for the oxygen to come. This is one path and this is another path. Okay, according to migratory aptitude, we say oxygen should attach to tertiary carbon, but here most steric hindrance is present. 4 carbons are there and 3 hydrogens attached to each carbon, so very much steric hindrance is present. Oxygen will not prefer to come from the steric hindrance, it will comes from here, and so the actual product in this reaction is this. So this is the trick number 5. Okay, next example is same. We expect the product in which oxygen should come from here, but the actual product is oxygen coming from here. So actual product is like this. So why this is the product? Because of steric hindrance. Here you can see more steric hindrance is present, so oxygen will prefer to come from here rather than coming from here. Okay, so this will be the product. So this is it for today. If you are having any doubts, any question, you can ask in the comment box, and you can follow us on Instagram, Facebook and Telegram channel for more updates, and you can share this video and subscribe to our channel. Thank you so much.